This chapter is called thermochemistry, and it's going to involve several different types of energy. The first energy we're going to talk about is heat, which is not the same thing as temperature, so make sure you understand the differences between those before we get started. Heat is the form of energy that involves a transfer, which means you can't just go to the lab bench and say, how much heat is in that beaker. You can say what is the temperature of it. You can talk about how much heat is going into it or how much heat is leaving it based on how many particles you have, what the temperature difference is. There's some variables you can use to calculate the amount of heat that's going in or out, but it's not just a measurement that you can go to the lab bench and just measure it. And the units we use for that are J or kJ, which stands for joules or kilojoules. The next thing is the law of conservation of energy, which is similar to the law of conservation of mass. It just says we can't create or destroy energy. All we can do is to change forms. So we can change from potential, which is stored energy, to kinetic energy, which is the energy of motion. And sometimes you're going to get some questions about the kinetic energy of the particles. So first of all, the equation for that is 1/2 mv squared. In this case, the m stands for mass, and the v stands for velocity. However, the units have to be pretty specific for this, so be careful in your homework problems. If it asks you for kinetic energy, check that your units are correct if you're not getting the right answer. The problem is that usually energy, we want it to be in joules or kilojoules, and this is actually a really good conversion or a really good association that you can know. And that is that a joule is the same thing as a kilogram meter squared per second squared. Those are the same thing. So what that means is that your mass needs to be in kilograms and your velocity needs to be in meters per second. So that when you plug all that in, you end up with kilograms meters squared per second squared, which is a joule. So you can put your final answer for that in joules. There's a few things about heat and temperature. So again, temperature is the motion of the particles. Heat is a measure of how much energy is going in or out of a system. And just be careful that heat always flows from hot to cold. So for example, when you're holding an ice cube on your hand, it feels like coldness is going into your hand. But really what's happening is that because your hand is hotter than the ice cube, heat is leaving your hand and going into the ice cube. And the sensation of cold is what your brain is telling you is what's happening. It means that heat is leaving your hand. And heat is transferred during a temperature change. The next part of these notes involve the word state functions. State functions means that it does not matter how you got there. So some examples of that are pressure. We don't care whether you pushed on something or released the pressure. We just want to know what is the pressure. So it doesn't really matter how you got there. However, Q and W are not state functions. We care where the energy came from, or if the energy is going into the system or out of the system. We don't want to put a reaction in a car engine that's not going to produce energy. If it absorbs energy, then it's not going to make your car go. So we need to know which direction the energy is going. So keep in mind that for this chapter, you're going to be using positives and negatives to show the direction of something. They don't mean greater than 0 or less than 0. They're just showing where it's going. So negative means it's leaving, positive means it's going in. All right, these next two words you saw in honors chemistry. So exothermic means that heat is leaving. Endothermic means that heat was gained, or it doesn't have to be heat, it can be any type of energy. We did a few graphs with this that we're going to go over in detail for this chapter as well, so let's just go ahead and review that. Exothermic is this graph. So if you start with the reactants and you end with the products, notice that you started with more energy, so we'll say this is the potential energy over here. You started with more energy than you ended with, which means heat was lost. For endothermic, it's going to be the opposite. So this time you're going to start with a low amount of energy and notice that the final energy is greater. So the products have more energy than the reactants. There's a few other things we may as well just review real quick on this graph. Keep in mind that from the reactants to the top of the hill is called the activation energy, and it's the energy that it's required to start the reaction. So in general, exothermic reactions have a lower activation energy. They still require a little bit of energy to get it started, but not nearly as much as endothermic. And so it's important to recognize that exothermic is favored in nature, which means it tends to happen more often in nature. It doesn't have to be a reaction to be endo or exo though. Physical changes can also be endothermic or exothermic. So for example, if you have a solid turning into a liquid or a liquid into a gas, anything in that direction requires energy. So we say that those are endothermic. So for example, a solid to a liquid would be melting. So if you put a piece of chocolate in your hand and you leave it there all day, it's going to eventually melt because it's gaining energy from your hand. If you boil water, it has to gain energy from the stove to turn into a gas. So those are all endothermic, and then the reverse is actually exothermic. So to get a liquid to freeze, you have to remove some of the energy of the particles. You have to slow them down to turn them into a solid to freeze them. So keep in mind that endo and exo can be, it can be a reaction, or it can also just be a physical change. The next thing is just a helpful conversion, and I actually posted in Canvas a whole list of some of the equations and things that you're going to use for this chapter. So hopefully that list, that's kind of a summary of all these equations, will help you. So keep in mind that 1 and 1.3 joules is equal to 1 liter times ATM. You're going to use that in your homework. Hint, hint. All right, let's get to some of these other last reactions for this section. So we're going to talk a little bit about heat and work, because the combination of these two is the internal energy or the system energy. So you're going to see E, which stands for the energy, and sometimes they use U for that. There's going to be a lot of variables for this chapter, so again, the summary that I posted in Canvas will definitely help you a lot. So first of all, the Q is equal to the heat. And you may remember this MCAT equation from first year chemistry. Let's just review that. The M in this equation is the mass. So it matters how much stuff you have. There's a Bill Nye that we watched one time in honors chemistry that talked about the difference in energy between a lit match versus a swan. And the swan actually had more energy leaving the system than the lit match, because the swan, it was an ice sculpture swan. It had so many particles, it was huge, that if you add up all the tiny bit of energy leaving each of those particles, it added up to more than that tiny little match, even though the match seems like it would be more because it's on fire. So the bottom line is how many particles you have makes a difference in terms of the heat. C stands for specific heat. And this is going to be usually in units of joules per gram degree Celsius. And this is a certain constant for each substance, because different things absorb energy better than others. For example, metals absorb energy really well. So if you have a curling iron or a pan on the stove, those metals are going to get hot really fast. Versus water, which has, so they have a low specific heat because it doesn't take much energy to make their temperature change. But water, it takes a lot of energy to make the temperature of water change. So for example, on a super hot day in the summer, you can jump into the pool and the pool water is still going to feel cold because it just doesn't have enough energy in the air to heat up that amount of water. So water has a very high specific heat, and metal has a very low specific heat. And then delta T is the temperature change. Delta means change in, and you'll end up with the correct sign if you can do final temperature minus initial temperature. So again, what you'll end up with is either a positive Q or a negative Q. And remember, the negative just means it's leaving, and the positive means that it's going in. So if heat is leaving the system, you'll end up with a negative Q. If heat is going in, you'll end up with a positive Q. The other part of this, the system energy, is called work, and work has to do with changing the volume. So notice that equation, work is equal to negative P times the change in volume. And again, you'll get a negative or a positive for this, and that has to do with whether you're doing work on the system or whether the system is doing work on the surroundings. So first of all, the system is like the beaker, and the surroundings is like the stuff around the beaker. Or if you have a balloon, the balloon and everything in it would be the system, the air surrounding the balloon would be the surroundings. And I actually just picture a balloon anytime I do this. If you are pushing on the balloon, then the surroundings are doing work on the balloon, and the volume would be getting smaller. If the balloon is pushing on the air, it's going to get bigger, so the volume gets bigger, and so it's like work is leaving the balloon. So depending on how the volume is changing, whether the balloon is getting bigger or smaller, that's going to affect the sign of the work. But again, negative work means that it's leaving, and positive work means that work is being done on the system. All right, so the next thing is enthalpy. And enthalpy we teach in honors chemistry as like the heat of the reaction, which it is, but it actually involves pressure and volume as well. The only thing is that if you have constant pressure, then the change in enthalpy, the pressure is just not part of the equation anymore. And we almost always have constant pressure. So whether you're doing an experiment in the lab or whatever you're doing, you're not usually changing the pressure of the room at that time. And so almost always enthalpy is equal to the heat of the system. And so we usually just refer to it as that. However, keep in mind the units. So you're going to see an equation at some point. You're going to see like A plus B yields AB. And then off to the side, you're going to see delta H equals, we'll just say 50 kilojoules. It's really tempting to think that that is in kilojoules, but it's not. It's actually, let's stick some numbers there. It's actually kilojoules per however many moles you have in the reaction. So it's a ratio. So for example, for A, it would be 50 kilojoules per 1 mole because there's a 1 in front of A. But for B, this is actually 50 kilojoules per 2 moles of B, because of that 2 right there. So that 50 kilojoules is not really an amount, it's an amount per however many moles you have from the reaction. So a lot of the calculations you're going to do in this chapter, you're going to be given either grams or moles, and you're going to use that to cancel this part of the fraction to end up with just kilojoules. And it's confusing because it looks like it's just kilojoules in the question, because again, it's going to only say kilojoules, so you have to know that it's actually kilojoules per mole. All right, so we only have 2 more topics for this chapter, or for this section. Let's skip down and do the delta H equals the products minus the reactants first. So this is one way that you can find enthalpy, and we're actually going to learn several different ways in this chapter to calculate enthalpy. So the way that you know which one to use is just by what information is given to you in the question. So what that means is that the heat of the products minus the heat of the reactants is equal to the heat of the reaction. It's kind of like when you do delta T, you say that the final temperature minus the initial temperature is equal to the change in temperature. So the heat of the products minus the heat of the reactants is equal to delta H. So what you will do is add up all of the heat of the products. You'll add all of these up. You're going to add up the heat of the reactants, and then you're going to subtract them. All right, and then the last thing, when you do that though, when they give you, so for example, if we go back to our A plus B equation, so they'll give you the kilojoules per mole for A, they'll give you the kilojoules per mole for B, and for AB2. So you would add up all of the products and subtract all of the reactants, but don't forget to multiply by the coefficients so you get rid of that unit of moles. So you'll do the moles times the number that they give you. And there's a chart in the back of the book that has all of the heats of the different substances that you'll need for the problems that you're going to do. So again, when you get that number, just don't forget to multiply it by the coefficient in the reaction, and then you're going to do products minus reactants. And just a couple more things in your notes. It's going to talk about C, which is the specific heat. However, there's different units that you can use for this. So in general, it's the amount of energy that it requires for 1 gram to be changed by 1 degree Celsius. So it's going to be units of joules per gram degree Celsius. We talked about that just a minute ago, but sometimes they can put moles here. So you just have to put your numbers in whatever units that they give you. So if they give you moles on the bottom over here, then you're going to use moles over here. And the next thing is the calorimetry. So calorimetry is the idea that the amount of energy lost by one thing is equal to the amount of energy gained by something else. And you can even plug in MCAT for the Q. So for example, if you take a hot piece of metal and drop it into a beaker of water, you can see how much the temperature changes in the water, that delta T. You can do the specific heat of the water, and you can do the mass of the water, and you can figure out the amount of energy that went into the water, and then you can assume that that's the amount of energy released by the metal. So as long as you're trapping the energy in, you can set them equal to each other. Just keep in mind that one is positive and one is negative, because the heat is leaving one thing and it's being gained by something else. And the very last thing is just be careful, and I highlighted this in the notes with a bunch of stars. When you break a bond, it takes energy. When you form a bond, you get energy. Make sure you highlight that in your notes. It's right, it's in section section 6.2. It's at the very end. It says when you get energy when you form a bond, and it takes energy to break a bond. So we're going to use that idea quite often throughout the whole year. And that is it for section 6.1 and 6.2.